The Poisson distribution is an interesting distribution, and we're going to talk about that in this screencast. Before we get started on this, I just want you all to say that word. It's pronounced poisson. It's a French word meaning fish. So that's how you pronounce it.
Les poissons, how I love les poissons! Love to chop and to serve little.
The Poisson distribution is when we have a continuous interval, but we have discrete events occurring. So discrete events occurring on a continuous interval. This interval can be something like time. So I show that here. The example I'm going to be going over today in this screencast is going to be earthquakes. Earthquakes do not occur on a consistent, regular period. It's not like we have a certain number of earthquakes every year or a probability of an earthquake every day. Instead, what happens is if we start our time, we might have an earthquake, later this year. We might have another one here. We might have one immediately after that. And so they're discrete events. The events are earthquakes, but they're occurring in a continuous interval, and that continuous interval is time. Whenever you have discrete events happening on a continuous interval, you should think about using the Poisson distribution. Another example where we might have a continuous interval would be physical distance. This might be potholes in a road. So you're traveling down this road, so there's your car, and occasionally you might hit a pothole. So the events, the discrete events, are potholes. So you might hit a pothole there. It might be a while before you hit another one, but then there might be a bunch in the next little bit. And so they're random occurrences, discrete events in a continuous interval. The interval does not have to be time or distance. It can be area. So maybe this is a silicon wafer. Occasionally on that silicon wafer, you're going to have defects. So you could have a defect there. You might have two over here. The event, the discrete event, is a defect, but it's in a continuous area. It's a continuous interval. And so this would be an example of where you might want to consider the Poisson distribution. Another example of a continuous interval would be volume. And let's just say we have a suspension of cells, and we have living cells and dead cells. And in this volume, you might have discrete events that are cells that are dead. So you might have dead cells that are in this continuous interval. The discrete events are dead cells, and the interval is volume. So let's just sum this up. The Poisson distribution is applied to situations where the rate of occurrence of discrete events is specified and is known. Usually the rate is a number of events per unit time, as I talked about, but it can also be in distance, it can be area, and it can actually be volume. This rate of occurrence is given by the symbol lambda. So lambda is actually the number of events per interval. That could be cells per cubic centimeter, that could be flaws per square centimeter, that could be potholes per mile, that could be earthquakes per year. The random variable that we model using the Poisson distribution is the number of events x that occur in the continuous interval, and the probability function is given here, and this is known as the Poisson distribution. It's important to know that in order for you to model this, you have to know the interval. This is given a capital T because we oftentimes model intervals over time, but this interval could also, again, be distance, area, or volume. But T is your continuous interval. If you were looking at the number of earthquakes in 2 years, your interval would be 2 years. You can't estimate things with the Poisson distribution unless you know the interval that you're considering. The mean and variance, interestingly, are exactly the same for the Poisson distribution. Based upon historical data, we know that in the last 40 years, there have been 200 earthquakes. The first part of this is what is the mean or the expected value for the number of earthquakes in the next 2 years? Well, to determine this, we can determine a lambda. Lambda is the background rate of occurrence, and this is we have 200 earthquakes in 40 years. So lambda is going to be 5 earthquakes per year. Now this is not the mean. The expected value or the mean also depends upon t and our time interval. For this problem, the time interval is 2 years, and the mean, going back to a previous slide, is given simply by lambda times the interval. So in this case, our expected value or our mean, is going to be 2 years, and we expect about 5 earthquakes per year. We would expect in 2 years to find that there have been 10 earthquakes. Let's go through the second part. The second part of the problem is asking what is the probability that there will be exactly 6 earthquakes in the next 2 years? Just like some of the other discrete probability distribution functions, the x value here is a discrete variable, and the output f of x is the probability of exactly x number of occurrences. To answer this, let's first look at our background rate. We calculated this as 5 earthquakes per year or events per year in the previous part of the question. Our time interval here is 2 years, so the mean or lambda t that goes into this function should be 10 events. And a lot of times we leave off the earthquakes, and that implies that we have events, 10 events occurring in the next 2 years. And if we plug lambda t into the Poisson distribution, we get the following, and we can plug this into our calculator. We get this to be about 0.063, which means in the next 2 years, there's a 6.3% probability that there's going to be exactly 6 earthquakes. Let's move along to part C. What is the probability that there will be at least 6 earthquakes in the next 2 years? Just like some of the other discrete distributions we've looked at, we can put together a histogram or a column chart of this. Graphically, at least 6 earthquakes in the next 2 years would be the probability of 6, the probability of 7, and we sum everything to the right of this. All right. Now keep in mind that in contrast to the binomial distribution, we can keep going forever. We could potentially have 100, and that's going to be very small, but at least you have to consider summing everything above that. That's very hard to do because you would have to add f of 6 plus f of 7 plus f of 8 all the way up to very large numbers. What's better to do and way easier is to calculate f of 5. That's the cumulative up to and including 5. And then we subtract that from 1 because the sum of all of these bars is going to be 1. And so that's what you can do. You can take 1 minus the sum of f of 0 through f of 5, which is also capital F of 5. Let me show you how to do this in Excel because it's way easier in Excel. Alternatively, you can just plug this into your calculator. So I'm over here in Excel. Let's just fill out a couple things. We had 5 earthquakes per year. That's our long-term average if we're looking at 2 years. And I'm actually going to add in here a cell for our mean. Our mean is just the product of lambda and our interval. That's 10. I'm just going to name that mean real quick. And let's go ahead and use the Poisson.Dist function in Excel. The first argument is the number of events that you're interested in. So that's going to be x here. The mean is our mean that we calculated above. So I type in our mean that we've named. And I'm going to use here the non-cumulative distribution function. That means the probability of getting exactly 0 earthquakes in the next 2 years is very, very small. It's nearly 0. Because of how I set this up, I can easily copy that down. And this is telling us that the probability of getting exactly X number of earthquakes per year. And you see that we get here 6.3%, which is what we got in part B when we worked it earlier. Now to answer the question of what's the probability that you'll get at least 6 earthquakes in the next 2 years, we would have to sum the individual probabilities of these 6 through 15, but I just stopped at 15. This would keep going, and there's a probability that you would have 20 earthquakes in the next 2 years, 30, and so on. So really, you would have to add all the bars beyond this up until, theoretically, infinity. Instead, we can use the cumulative Poisson distribution function. And again, this is going to be 1 minus f of 5 because we're being asked at least 6. So we're going to take 1 minus up to and including 5, which is the cumulative Poisson distribution up to and including 5. And so I can just do 1 minus the Poisson distribution of 5, because we're interested in x equals 5. The mean is our mean that we calculated, and instead of false, I'm going to use true. So it's a cumulative. And when we do that, it's telling us that there's a 93.3% chance that we will have 6 or more earthquakes in the next 2 years. Hopefully, this screencast gives you a better idea of the Poisson distribution and how to implement it in Microsoft Excel.